make the boundaries too wide, we won't get ready with estimating the resilience before the disruptive event has taken place, and we will never end calculating. So this is a dilemma, of course, for engineers, but also for other disciplines. And I'm very happy to be able to welcome now a professor for land use engineering, the director of Future Resilient System Program at the Singapore ETH Zurich Center, and a member of the ETH Zurich Risk Center, Professor Hans Heinimann.
Yeah, thank you for the warm welcome. As we already heard quite a bit today about resilience, and I'm very happy to share some of our ideas that emerged in Singapore, what's going on. And I put my talk about can we build robustness and resilience into complex systems. I think we heard that. That's probably a key issue. Let me make a couple of remarks before I start. The first thing is, in our understanding, resilience is not about risk management. Resilience is about strategies and tactics to cope with ambiguity and unexpectedness. Things you don't expect, things you cannot quantify. That's why we need resilience. The rest we can use risk management. It proved to be very useful. So it's like a spaceship that was designed for certain pressures, temperature, and so on. You fly out in space, and you come into an area where something happens. You have a huge electromagnetic field, and if the system still works, then it's resilient. So coping with cases when the assumptions for which the system was designed are wrong, that's resilient. The second thing is, I would like to mention, I really had the privilege, and what I can present here, it's the outcome of working with about 60 PhD students and postdocs during the last close to 5 years. We covered the whole range from theoretical physics to psychology, cross-disciplinary, so I could also talk a little bit about the social aspects, but I will mainly focus more on technical issues. My guiding idea is mainly to focus on complex systems and their behavior, and this is my plan. I think it's, we heard that many times today, it's a problem of the lean tower of Pisa. Some people say, oh, it's leaning to the left side. Others say, no, it's leaning to the right side. So it depends what your perspective is. So you have to know my perspective so that you can understand how I'm looking at it. The complexity issue and the resilience issue. Then I would like to address one thing that I think was not very prominently discussed. Complex systems show regime shifts. I learned that in history in high school, that you cannot explain history of the future based on what happened in the past. This has to do with emergence, with regime shifts, and history is full of regime shifts, and what happens in complexity is full of regime shifts, so we cannot predict it. The next thing I would like to illustrate a little bit, some example, how we are approaching. It's networks mainly, road networks, how to manage road networks as a whole, because networks as a whole has property. And finally, building resilience, just two things. It's about robust and flexible design and about an orchestrated, systematic transformation process. And I would like to share that a little bit, how this looks in an urban environment, or could look. What is complexity? My first thing, it has a couple of dimensions. The first thing, it's interconnectedness. Parts in a system are connected. And this is why risk management and risk assessment doesn't work, because the assumption is that what you observe on single events is independent from each other. So you will always underestimate the real risk if this assumption does not hold. Then the second thing is complex systems have some goal-seeking behavior. And homeostasis is a special case of goal-seeking behavior. So it adapts in a certain direction. It's driven in a certain direction. A third ingredient is adaptive. Adaptive in a sense, I can change my goals, I can change my behavior, I can change my strategies. So it's not constant in time. Then maybe the most important thing, there are feedback loops, and those feedback loops are changing the goal-seeking and the adaptive behavior. Then we have delayed response. Those who played a little bit with system dynamics know that this effect is very strong. Some physical entities have the property that their response is delayed. And if you have many things interconnected, this creates very complex patterns. And finally, this is more or less an outcome. Complex system has emergent behavior. This means you cannot explain the behavior that you will see in the future based on the data that you have from the past. This limits a little bit what we can do, and it's not very encouraging, but I think we have to be aware that's reality. Let me now look on just two cases. This is the big financial crisis in the US, the failure of the banking system. And I think if you look at this video, you can immediately see it has something to do with, it's not about a single bank. It's a phenomenon that things are happening in a certain sequence, so it's a systemic problem. It's a systemic problem, and how to manage this is still a big problem in financial engineering and science. It's not solved until today. How to make the financial system more robust in the long term is also a resilient problem. So you see 350 banks and about 650 billion losses with a very, very short time period. Definitively, this event, nobody could prevent it. Nobody. It just is there, and then we have to cope with it. It's a typical situation to cope, to look from it as resilient. Then I like this, look a little bit at this video. It was run, this experiment in Japan. Everybody has to drive in a circle and to keep constant distance to the driver in front of it. And what you can see here, after a very short time, the system starts to oscillate. And after a certain time, you even can see that some of the cars stop and start again. Now, there are two ways to look at it. The first traditional way is, you say, from a single driver's perspective, the problem is I have a stupid driver in front of me. This is the first thing to explain this phenomenon. The second one is, of course, you say it has to do something with the interaction and with the adaptive capability of the drivers. I think it nicely illustrates what a complex system is, and of course you cannot predict it. There's no way to predict it. I think this is the type of phenomenon we have to cope with. Then, why is the world moving into more complexity? This smartness movement is going on, and smartness means putting cyber-physical systems more and more into practice. Every cyber-physical system combines a traditional physical system with a control system, and the control system has always three components. You have sensors, they sense the state of the system. Then you have a controller who somewhat knows where the system should be, looks where the system is, and then initiates some corrective actions to bring the system back through actuators. DoD in the US coined the term cyber-physical human systems. They even go one step further. And if you look at that, it's more on algorithms, it's more on capabilities. It's about, for example, things like shared perception. The human beings are no longer the only ones who have a perception. Machines have also perceptions. Machines have a mental model about reality. I will come back to that. It's about shared decision-making. Only a few decisions are made anymore by humans. Others are made by machines. So many, especially in the financial sector, fintech. It's about shared learning adaptations and so on. So And this is ongoing. Let me just show one thing to illustrate a little bit what that means. This is the number of lines of code that are around computer code. On top you have Google. Google operates about 20 billion lines of code. Even if you have the most reliable and secure software system, it's never possible to do that fault-free. You always have some stuff in, and you have legacy. All those huge amounts of codes have legacy parts in it, and some of the parts is no longer understood. My brother is a software engineer in the banking sector, and he always tells me you wouldn't expect how many applications still running on COBOL code. Many people don't understand yet what that is. It was a programming language of the 1960s. And if you look on the second thing, a modern car has 100 million lines of code, what you just buy out of the shelf. So it's a lot of this stuff is around. And if you look compared to that, the space shuttle, how many lines of code the system was it just disappears. I think that's a little bit to get a sense what it means, and it will increase. It's incredible. It's incredible. This digital revolution that's going on, and it just started brings an additional level of complexity. Now our resilience framework. We look at 3 classes of functions. And it's generic, you can transfer that to any system. We heard a lot about the biophysical world. This is the typical things we always talk about. I will come back to that. But every system has a cognition, either in part of an operating organization or of users that use where the system is and then can react, or in a modern sense, an automated system that creates this type of cognition. And of course, we heard that also. You have also enabling functions. This means enabling a system to cope if something happens in the future. Now a little bit in more detail. Of course, the first thing in the biophysical part is resist within acceptable limits of degradation. Secondly, stabilize critical functionality. Rebuild functions up to a certain limit of level of functionality again. And then number 4, it's not adaptation, it's reconfiguration. And I think the Christchurch example is a typical example. You don't just build the system back where it was, you reconfigure it. Especially if something happens that really is severe, you reconfigure. And we should look at that as an opportunity. I'll come back to that. This is an opportunity in each event to reconfigure. This goes along all the time with the cognitive components to stay aware all the time. It's not so easy, especially if for a long time nothing happens. Then I have to, maybe some of you who are economists, they don't like that. It's not about decision making. It's not about decision making, it's about sense making. It was happening, what happens before you make a decision, to create a picture, what is going on now, not to map it into predefined picture, but what is going on just now. And then based on that, you can make decisions. But the critical part in resilience is sense making. Sense making is really a crucial part. I could give you a couple of examples where it went wrong. Then respond. We can look at the immune system. The immune system has a whole range of responses, and everything that proved to be useful in the past is still available. Doesn't get lost. That's the big advantage of the immune system. And then the update and adapt also. The immune system, if it encounters something, it learns out of it. And this tells us also we have to stimulate this cognitive function again and again and again and again. If you don't stimulate it, some of the functions are getting lost, and that's the big challenge. This is the way we see resilience. You can look at that also for other systems like social systems. If we take, for example, the recent tsunami that just happened in Sulawesi. The social functions and structures get disrupted. So the issue is the same. You have to make sure that the social functions don't degrade too much, that you restabilize them, that you rebuild it, that you reconfigure it. It's exactly the same. That's about the social part, to stay actionable. That's the real crucial issue that matters in resilience. Let me just show one example of it's the so-called Koon train collision. The Singapore underground system is fully automated. There are no drivers. But two trains collided. Why did this happen? Nobody could predict it because there were 6 systems talking to each other, 2 signaler systems, 2 control systems, 2 scheduling systems. And at some point, there were some wrong assumptions. And I was just thinking, when I go to Italy, I'm aware that they have a different approach how to handle, let's say, the signaler system on the road. And I don't fully trust the signaler system, but I also look. So this is also an issue about trusting each other. And this is something that's a big issue in software engineering, to develop trustworthy system. For example, the Illinois group that is here, they are working on trustful, secure cyber plexus. This is a big issue with automatically reconfiguration and things like that. Another system, just a sense-making system. So this Koon train accidents definitively has to do with a wrong sense-making system. It's wrong in the sense-making. The system had a wrong idea what really is the matter that is. It was wrong. I would say what we're discussing just now, the 737, it's very similar. You have an automatic system, we have the pilots, both have a picture of the reality. One doesn't trust the others. The automatic system doesn't trust the pilots. The pilots cannot do anything, but if they would do this mental model together, maybe we would be much better off. Now let me come to regime shifts. We can characterize complex systems with 2 dimensions. One is heterogeneity on the x-axis and coupling strength on the y-axis. And this blue domain is called self-organized criticality. This is the domain where traditional risk management with extreme value statistic is valid. It's only valid in these assumptions. And you can imagine that you have a sand pile and you drop single grains on this sand pile and look the avalanches, and then make a statistical analysis of the length of the avalanches and make a prediction what is an upper limit of an avalanche that can happen. That's the way risk management looks like. What we do is we push the system to the left side. We decrease heterogeneity due to standardization. It's one of the major drivers. But we also increase coupling strength, so this means that there's a tendency that the systems move in a domain where another regime is true, and this regime is, we call it a Dragon King regime. I will explain you in a minute why this is called Dragon King. It's because of the black swans. Nassim Taleb coined the concept of a black swan. A black swan is still within the self-organized criticality regime, but is far out in the tail. It's not a different process. It's still the same process, where an outlier, a Dragon King, is something totally different. Just to complete the zoo, we talk about black elephants. Howard Kuhnreuter wrote a book about black ostriches. The Chinese came up with a gray rhino. It's interesting, not black, but gray. It has something to do with Chinese culture. We could talk a little bit more about that. So if you want to become famous, you have to add some animals to the zoo. Then you will become well known in the risk management sector. And again, what happens in this other regime, we cannot predict it. We cannot predict it. That's the main message. Let me show an example. We don't really understand how networks, large networks, grow. And this is an example of the city of Zurich. It's not a really large network. There's 10,000 nodes and about 20,000 edges in a range from 1955 to 2012. And what you can see here, the darker, the more important are the nodes of the network. You see some slight changes, but the interesting thing is there's a measure in complex networks here. It's called betweenness centrality. The 1955 case, the distribution function looks something like that. If you look at the 2012 case, looks like that. Now what we see, people working risk management, it tells something. It gets more heavy-tailed. Distribution gets more heavy-tailed. This means that you have some parts of your network that are becoming more critical for the whole network to keep the capacity of the network quite high. So this is an aging effect. We were also looking, can we see a similar effect if we strain this network, for example, with flooding? And you see the baseline condition here, and you see the flooding strain. Exactly the same picture. The distribution gets more heavy-tailed. And I think that's an indication how we can characterize how complex networks evolve in time. Let me show another problem. That's if you have a system that has many resilience cycles, drawdown, draw-up cycles, like a financial network, a financial system, and if you use some of the metrics, sorry, Michelle, the traditional triangle approach doesn't work very well in a situation like that. You have to adopt this metric, and this already shows metrics are always a little bit problematic. They're context dependent. And what we see in terms of resilience index, you see it's not a constant property in time. It changes all the time. So are we able to say a system is resilient or not resilient? No, if you look at that, resilience changes. So it's itself a distribution, something like that, a distribution function, which is, by the way, following a power law distribution. This is interesting, what we probably would expect if we look at it from a complex network theory point of view. Then here, three different networks. Left-hand side loosely coupled, and on the right-hand side a very strong coupled with one effect. I would say it could be the Thailand 2011 effect, where, for example, you have in Japan manufacturers that rely on suppliers in Thailand, where you have long-distance links in your network, not only neighboring links, but long-distance links. And the interesting thing, if you strain those networks, how do they behave? The left side is the subcritical stuff. Then we have a typical power law case, the self-organized criticality, and now the supercritical, which is also very interesting. You see, it starts bumping in the tail. And that's exactly this type of complexity, what we see, which you cannot predict. So that's a phenomena of complexity that you find in relatively simple arrangements. And you would agree with me, many real-world systems are much more complex than what I show here. So even quite simple things show this type of stuff. Let me share another thing. It's the influence of repair tactics on recovery based on a case study done in Nepal after the earthquake. This is, let's say, a 9-to-5 approach how a system recovers. You very often see that repair teams start to repair following a proximity approach. They just start the next place where you can repair something. But if you think to do that in a smart way, you minimize proximity plus repair time somewhat combined, and you have an overall tactics how to do that. You recover much faster. So this means the recovery function always depends on your tactic, your strategy, and your resources. If you have a huge event, the available resources matter. So this makes the prediction of recovery even more difficult, just to consider that. Let me now come to how to build resilience. The first thing is building, you see that's on the x-axis, the assumptions on the design variable side. You can have certainty assumption or uncertainty assumption, but also in the objective function you design a system for, certain, uncertain. The traditional engineering approach is here, certain assumptions and certain objective function. If you relax design variables, this is what is called a robust approach. This means you look for a good solution, but under the constraint to be feasible within all uncertainty sets. And this is not available at no cost. There is a cost trade-off. You have to be aware of that. You can even go one step further. If you relax the objective function, it's flexible design. So that's a general engineering approach that originally came out of MIT, and it was strongly linked to military research. I'm going to show you an example of that. The B-52 bomber was designed in the late 1940s, and it will be taken out of service in 2044, so this means it will fly for 90 years. It's amazing, it's amazing. But of course, the type of engagement and things like that and adaptive capability is amazing. It still is used. The other example is the B-59. It was a supersonic bomber. It was based on two very limited assumptions. It will fly higher than any Soviet anti-aircraft weapon, and it will fly faster than any Russian interceptor aircraft. It took about 5 to 7 years, unless the Soviets figured out how to do that, they overcome that, and then the whole fleet became obsolete and had to be taken out of service within a very short time. So you see, it was even not 10 years in operation, a whole fleet close to 100 airplanes. That's an example a little bit also in this direction. Now let me come resilience as a transformation process for a city. This is an outcome of a discussion with many agencies in Singapore, because we realized one agency, it's called the Urban Redevelopment Authority, they said, well, if we talk to the water guys, they tell us we have the most resilient, reliable, efficient, eco-efficient water system in the world. Then we go to the transportation system, the same. Then we go to the building system, absolutely the same. But how does this add up into an urban system? And we came up with 3 layers that would have to be addressed to build resilience into a system. The basic layer is, what is the best land use allocation to make a system more resilient or more robust? That's the first layer. And of course, this scale is usually done by common sense. We could do that by mathematical optimization, and it would probably reveal new insights how to do it. Then the second thing is lifeline infrastructures. What I wasn't aware so much, lifeline always follows land use. It always follows land use. And the lifeline infrastructure is also how to extend it, how to re-engineer it, that it moves in a better direction. And then the third layer, the most influential one probably, you have cells where you can manage the building stock. And you have a first option, should we maintain these cells? Should we rebuild? Or should we redevelop? And this is somewhat an overarching framework how we think a transformation process in a long term could a little bit be guided. Let me make an additional comment. There is a historian in Switzerland who investigated all the big natural catastrophes from the medieval times until the modern times. And he found out, he said, You have to have a plan, and you have a window of opportunity immediately after something happened of 2 to 3 days. When you come in with a plan, it will get realized. So we should think about things like that, and then if something happens, come with a useful plan and to make the system better. What you see, for example, in Sulawesi, what I mentioned, it's exactly rebuilt the way it was before. And statistically, the same will happen as it happened just now. This is unfortunately what we have to expect, but it would have be a chance to really reconfigure the whole system in a certain direction. Some pitfalls. We talk about complexity, and I see in many ways this answer to complexity. You see that also if you're a little bit looking around, people talking about complexity, and then they come up with 3 indicators on a scale 1 to 5 that you say, okay, the first is 3, the second is 2, and then you add it up and say, okay, it's resilient or it's not resilient. I think this doesn't fit to the real problem. But this is, it happens unfortunately very often. Let me sum up. I think the whole thing about complexity is we have to manage the ingredients of complexity if we want to really address it. And in interconnectedness, we have to manage topology in a longer term, in which direction it goes. Then the next thing is organize for sense making, not for decision making. This is very crucial, organize for sense making. The next thing is robust control. This is probably going in direction distributed fault-tolerant learning. And also we can detect and anticipate Dragon King events by looking into real-time data streams. This is a possibility to do it. And orchestrate systematic transformation. This is what I wanted to share with you. Of course, later I'm happy to answer more questions. Thanks for your attendance.
I think we can allow questions also now, before we go to the whole panel. Okay? Do I see questions in the auditory? Maybe I have one to start. Hans, you said organized for sense making. There it is still, not for decision making.
Yeah.
I have not enough examples to relate something to it.
Well, maybe let's go back to the case where research started to look at sense making. It's a so-called Mann Gulch forest fire. It's well documented in the internet. It was a fire, and the US Forest Service had to fight it. And I think 15 fire jumpers were set up. And then they started, and their assessment of the situation was it a so-called 10 o'clock fire. 10 o'clock fire means it will be over at 10 o'clock in the next morning. But there were a lot of weak signals that it's not a 10 o'clock fire. So they immediately mapped the situation in a predefined mental model. And in the real end, I don't know the number anymore, many of them died. So it's mainly to focus on what is now. This is why it's called mindfulness, because in psychology or in meditation, mindfulness means to focus just on now, not on what was and not about expectations for the future, just look at now. And it's sometimes very difficult. I see that myself. We are so have such a high predisposition to map all the time things into categories that are somewhat in our mind.
Thank you. Further questions? Benjamin, there we go. Yeah, Ben, to start with. Where is the other one?
Very shortly, how to anticipate Dragon Kings if they cannot be anticipated? I didn't get that.
Yes, a colleague of mine, Didier Sornet, has been working on that. And the whole story started with the Ariane 5 rocket failure in the first launch. ESA gave all the data out, and they asked, could we have anticipated that something goes wrong? And he was looking at the noise of all the signals. So it's only working if you have real-time data streams. Otherwise, you have no chance. And the time granularity has to be adequately. Then you can anticipate that something happened. There are about 6 to 7 mechanisms that we know, but we don't really know which mechanisms is adequate for which system. That still is further research. If you're interested, the tools are available publicly. I can give you the tools.
There's one question in the back, and then Steve. Yeah.
Hi. So your example about the lines of software code, was your message there that unnecessary complexity tends to emerge in the way we manage systems? And looking at the lines of software code, could you classify as those into which are essential, which are necessary, which are unnecessary, and which are kind of legacy junk? And could you use that analysis to simplify the system, or is it very much a one-way path from a simple system to a complex system that we can't really reverse or wouldn't want to?
No, I think legacy systems is not junk. If you look into the banking system, very many applications, and my brother told me that, for example, the software in some countries in Europe for the ATMs was just recently upgraded, and before it was an application designed in 1995. So it was running more than 20 years, and this due to commercial reasons. This is why you have paradigms that were different from what we have nowadays. There might be incompatibilities with other systems, and so on and so on. But I think the other thing is just a reality. That more and more of software is around, more and more software is interacting. Just look on your cell phone. Cell phone is a super example. Everybody has 30, 40 programs. It's highly connected to anywhere. And yeah, you can do banking and whatever, online shopping and things like that. Other people are reading what you have on your cell phone. You don't realize it. That's reality.
Mm-hmm. Steve?
One of the things I'm trying to think my way through is the reliance on complex system is really an act of trust to a point in terms of the users who don't often understand the complexity. When we start to see because something's gone wrong with it and there's risk being manifest by the system potentially failing, I'm thinking a bit of the Boeing case is a bit on this, then the response is in the political arena and actions are taken which may further accelerate some of the failures or not be well managed. I'm just, where do you bring in that what's that trigger point where now you have external, political response, taking actions that are either undermining, accelerating the cascading failure in some cases, or hopefully taking some productive action. Where does that fit into the regime here?
Well, if I would have an answer, I could probably make a lot of money. But
Steve wanted to make money.
The political, in my understanding, the political system itself is a complex system. And you have emergence. If I look around, many things that happened in the political arena internationally, nobody is able to predict actually how this would come out. And I think we have to take this more or less as a reality. What is a bigger problem we have been discussing, it's also a DoD project. The legal system does not allow us to cope with this fast development because the legal system is always based on a history 10, 15 years back. And there are trends to think about smart regulation. Could we have something that this regulation is automatically updated by machines, especially in the financial sector? And if you're interested, DoD did some research on this based on swarms of drones, where drones have contracts with other drones, and those contracts are updated in time. So I think it's not fiction, but it's ongoing research in this direction. I have a colleague who is a lawyer working in financial law. He says we have to do something. There's no way that the movement with fintech is so fast. The rules we have, they don't fit to the problems. And I think it's many areas probably like that.
So I see no more immediate questions and ask the members of the panel to the floor